Hello and welcome back to Basic Topology, the video series where we talk about topological concepts that we need in analysis and other parts of mathematics. And indeed, in today's part 10, we will show that compact sets stay always compact under continuous maps. This means that the image of a compact set is also compact. However, before proving this result, I first want to thank all the nice people who support this channel on Steady, here on YouTube or via other means. And please don't forget, with the membership on Steady or Patreon, you can download a lot of additional material for the videos. For example, you can easily download the PDF version for this video here on my webpage. And then without further ado, let's immediately consider a topological space X. This means we have a set X together with a topology Tx. And please recall, a topology is a collection of subsets of X that we call open sets. And now on the other hand, we can also consider a second topological space Y. And in addition to that, we also want to have a map from X into Y, which we call F. And now for what we want to do in this video, we need to have a continuous map between topological spaces. And as you already know, the definition of continuity is quite simple. We just have to consider open sets in the topology of Y. And then we just bring it to the left-hand side and look at the preimage of B. And then the only thing we need is that this one is also an open set. This is all, and then this definition guarantees that if we look at a point here in the set Y and a neighborhood around it, then the preimage of this neighborhood is a neighborhood of the point X on the left-hand side. Therefore, you could see this definition as the abstract version of the epsilon-delta definition of continuity as you know it from real analysis. And therefore, we also get a similar result if we consider compact sets. So what I want here is a compact set in the space X, so a compact set on the left-hand side. So let's call it A and let's map it to the right-hand side. This means we now look at the image of A under F. And the notation we have for that is F of A, but I use brackets to make it clear that we consider sets here. And now obviously under a general map F, a lot of things could happen to the image F of A, but now we consider a continuous map F. And now the nice result is that the property compact for a set A remains under a continuous map. So we can just conclude that the image is compact in the topological space Y. This is a really important result that we can always use when we have continuous maps involved. However, before we can prove it, we first need to talk about some general results for images and preimages. This means we can just forget about the topologies for a moment and just consider a map between sets. So we just have a mapping from X to Y, and F has no more properties than that. And you know this is enough to define images and preimages. So maybe let's start with an image, so we consider a set A on the left and map it to the right. So quite a similar thing to before, we just take a set A, which is a subset in X. Therefore, the image of A under F is well defined. And by definition, this will be a subset in Y. However, now let's say we make the set A smaller on the left-hand side. So let's simply say there we have a subset A tilde. And then the conclusion is that the image on the right-hand side also gets smaller. Hence, we also have the subset relation in Y. So not so surprising, and it immediately follows from the definition of the image. And now on the other hand, we also have this for the preimage. So if we have two sets, B and B tilde on the right hand side, we can look at the preimages on the left hand side. And also there by definition, the subset relation remains. So these are two things you can immediately remember. The image and the preimage conserve the subset relation. Moreover, both things also conserve unions. This means if you look at the image of a union of sets AI, then it's totally allowed to just pull out the union symbol. So more precisely, this will be the union of the images of AI. So quite a simple rule, but definitely something that requires a proof. So I would say, let's start with an element y from the left hand side. So y is an element in the image of the union, which means we can use the definition of the image. And this is quite simple, it just tells us that there exists a point x that is mapped to y. So we have an element x in the union with the property that f of x is equal to y. So this is the definition of the image, and now we can use the definition of the union. And indeed, the union just tells us that there is at least one fixed ai where this x lies in. In other words, we find an index I in capital I such that x lies in ai. And now this helps a lot because this last part here just means that y lies in the image of this specific ai. And moreover, now you see this is just equivalent of y being in the union of all the images. So in summary, we have here that all the arguments work in both directions, so both sets here are actually the same. So the proof was not so complicated, and now it might not surprise you that we have a similar thing for the preimages. This means the preimages are also stable under arbitrary unions. So now we would take subsets in Y, so let's call them Bi, and we look at the preimages in X. And the claim is the same as before, we can just pull out the union altogether. And now I think we can be quick with the proof, we just use the same arguments as before, but now the definition of the preimage. Hence it means X lies in the preimage if and only if we find a Y in this union. And then of course the property is the same, we want that X is mapped to Y. And then in the next step we can do the same as before, which means we find a specific index I from the union. But then what we have here on the right just means that X lies in the preimage of Bi. And this is all we need to conclude that this statement here is equivalent to the statement that X lies in the union of the preimages. So we didn't need any new ideas because everything came down to the definition of a union. However, now in the next part, I want to use the image and the preimage in a row. So more precisely, I have the image of the preimage of a set B. Now the notation might suggest that you can just cancel the two things and you get out B. But there I can already tell you, in general, this is not correct. It's also quite easy to see if you look at a general picture, so here would be our set B. Then forming the preimage gives us all the points x in X that are mapped into this set B. And in fact, into is already the key word because it does not mean that we hit all the points on the right just with the preimage. Simply because we don't assume surjectivity for the map, there might be points that don't get hit by the map at all. And therefore the only thing we get here in general is a subset relation. As the picture tells us here, we still map into the set B. So let's quickly write down the proof of that. So let's start with an element Y in the image, which means we can use the definition and find the corresponding X. And as always, this just means that f of x is equal to y. However, now we can also use the definition of the preimage, which means for this x, we find the corresponding point on the right hand side that lies in B. So in short, we can just say for this element x, there exists an element y tilde in B with the property that f of x is equal to this y tilde. However, from before, we still have the claim that f of x is also equal to y, which means y and y tilde have to be the same point. This immediately follows from the definition of a map. Each point x is sent exactly to one point y. So we have y is equal to y tilde, but y tilde lies in our B. In other words, we also have shown that y lies in B, and this completes our proof. And now finally, the last point I want to make here is to consider the preimage of an image. So roughly the same idea as before, but now the other way around, and there we can see that the preimage could be bigger. Also, this might not surprise you because we don't assume injectivity, so going back with the preimage could result in a bigger set. But also there, let's quickly formulate the proof of it. So we start with x in A, and then we want to show it also lies in this preimage. But this is quite simple because by the definition of a function, we know that there exists a y in the image such that f of x is equal to y. However, this immediately means by definition that this x lies in the pre-image of f of a. So there was not much to do here, and please also check that in general we don't have the other subset relation. Okay, so this was a lot of preliminary work, but now we can finally go back to topology. And please recall what we have are two topological spaces and a continuous map between them. And now the claim is, if we take a compact set in X, the image in Y will also be compact. And there please note, this works in this direction, so we work with images and not with pre-images. Moreover, please also keep in mind that in general we have two different topological spaces involved. In any way, the claim is always correct, so compact sets are sent to compact sets. And now we can immediately go to the proof, which is not too complicated because we have already done all the groundwork. Indeed, we can just copy the picture from before, and now we want to show that the set here on the right hand side is a compact one. And there you can recall the definition, which means that any open cover of the set has a finite subcover. So we just have to take open sets ui in Y that cover the whole image f of a. And with the formula, this just means that we have a union of the ui as a superset for f of a. And now obviously the only thing we can do here in the proof is to translate everything to the left hand side, because there we already have a compact set. And in order to shift everything to the left hand side, we have to use pre-images. Hence we just apply the pre-image to this formula. And as we have discussed before, the pre-image will not change this superset relation. And this implies that here on the right hand side, we actually have the image and then the pre-image applied to it. And as we have discussed immediately before that, this is always a superset of our set A. So we already have the set A on the right hand side, and on the left hand side, we can pull out the union symbol. There we actually have an equality, but the important result is that this is a superset of A itself. And moreover, by the continuity of F, we also know that these are open sets in X. So together, this simply means that we have an open cover for the set A. And at this point you might already guess, we can use the compactness of A to go to a finite subcover. This means we only need a finite union, and let's call the index set I0 to cover the whole set A. So as always, when we talk about compactness, I0 denotes a finite subset of the original index set I. So this is really nice, but don't forget what we actually want to prove. We want to cover the image here on the right hand side. This means we have to translate this finite subcover from the left hand side to the right hand side again. And clearly we can just do that by using the image on both sides of the formula again. So on the left hand side we have the image of the finite union, and on the right we just have the image of A. So it looks like we are almost there, we just have to pull out the union a last time. But there we know we can do it, and we even have an equality. And now what remains inside is a combination of image and pre-image, and there we already know they don't cancel completely. However, as we have proven before, it's definitely always a subset of the original set inside. So what we get here as a result is the finite union of the sets ui. And moreover, they still cover the whole image f of a. So after starting with an arbitrary open cover of the image f of a, we ended with a finite subcover. So we always find a finite subcover, which means that we have a compact set. So that's exactly what we wanted to do, and the proof is finished. So please remember this important result: continuous images of compact sets are always compact. And with that I would say it's good enough for today, and I really hope I meet you in the next video about topology. So have a nice day and bye bye.